Alright, so we got 3 topics today: B and T cell activation, Anergy, and Immunoglobulin Isotypes. We'll start with B and T cell activation. So this is going to be just really simply put, but what we need to understand about both B and T cell activation is that you need 2 signals in order for this activation to be complete. So first, with T cell activation, so the first thing is you're going to have a dendritic cell, or any kind of antigen-presenting cell that has a processed antigen. So you can see here, let's just say this is like a viral particle or something. It comes in here, the dendritic cell breaks it up, and then either presents it on an MHC1 or MHC2 molecule, and it presents this on the dendritic cell surface. So we got this T cell roaming around, and then it comes up and it has what's this here, TCR, the toll cell receptor. This is the guy that's going to latch on to the MHC molecule and recognize the antigen. So this right here, MHC to TCR, this is the first signal. And this is like a co-signal, CD4, CD8, depending on what type of T cell, helper, or cytotoxic cell. So this is the first signal. Now, this activation isn't done yet because we need this guy over here, the second signal. Now, okay, when we have like a generic T cell, one that hasn't differentiated between CD4, CD8 yet, they all have toll cell receptors, and they have CD28. So when you don't have a CD, or actually if you have both CD4 and CD8, then it's an immature cell. It's only when one or the other is present, then you have a mature cell. But an immature T cell will always have CD28 and TCR, because those are indicative proteins on a T cell. And the function of this CD28 is to bind with B7. B7 is present with dendritic cells like we see here, and on B cells. Let me just fact check myself real quick. I'm pretty sure it's yes, B cells, macrophages, and dendritic cells. Okay, so antigen presenting cells also have this B7, and this second message is what will actually will give a co-stimulatory signal, if you will, and this will activate the T cell. And what the T cell is going to do then is going to produce cytokines. And so these cytokines can either help with killing virally infected cells, or they can help with neutrophil chemotaxis, so they get some help with killing cells. So this is the first, this is the activation of the T cell. Any questions?
I would just say one other thing is immature T cells would also have a CD3 positive, along with the CD4, CD8, and TCR.
Right. Good call. So before this process happens, what is this T cell called? So once this activation occurs, it's a mature T cell. What's it called before then?
Naive.
Naive T cell, very good. Okay, so then we got the B cell. So we have the B cell. Okay, actually, before I continue, what do B cells make? What is their job? Antibodies, immunoglobulins, right. So basically, I talked about T cells first, because once this first pathway is done and this T cell has been activated, now he's going to come over here. And essentially the first part of B cell activation is you need an activated T cell. So this guy just came over here, and this T cell is already activated, but it has, and as you can see, it's got these cytokines that's given off, but it has that original antigen that was presented to it by this dendritic cell. So now T cell wants to come over, and it, with its toll cell receptor, excuse me, presents the antigen to the B cell's MHC2 molecule. And so this is the first signal. But the purpose of the activated T cell binding with the B cell is it wants to tell this cell, based on whatever this antigen is, like, hey, this can cause an allergic reaction. Let's make some IgE. Hey, we want to switch from IgM. So we're going to eventually end up in class switching. But we only have this one, this first signal. The second one here is CD40 and CD40 ligand binding. CD40 ligand being on the T cell, CD40 being on the B cell. So this is, again, the second signal. And once this happens, again, the activated T cell, now even more so activated, is going to again secrete cytokines. But this time, the difference in these cytokines versus these cytokines over here that we had is that the ones over here were to help kill viral cells, help to neutrophil chemotaxis, whereas over here, these cytokines are going to tell this B cell what type of class switching to undergo. And obviously from there, the B cells are going to spew out whatever antibodies it is influenced by, whichever cytokines is thrown at it. Any questions on? Okay, so if we have a patient with a messed up CD40 or CD40 ligand, what pathology might we see? Wish I could make a red X over here.
Is that Anergy?
A gamma globulin
Davey's on the right track. Tulsi, you're on the right track. We'll talk about that in a second. So, yes, but there's a specific pathology associated with CD40 or CD40 ligand, either deficiency or this.
So the only thing you'll be able to produce is IgM. So you can say it's hyper IgM syndrome because you can't switch classes. So you only produce one class, which is IgM.
Correct, sir. You have hyper IgM syndrome because you don't get class. Very good. Okay, so Tulsi was just talking, or mentioned the term anergy. And anergy is essentially when you have only one of your stimulatory signals occurring. You don't have the second one. Let's just say here it's, I don't even know what it was, CD28. Let's just say CD28 is missing on the T cells. And you only get one stimulatory signal. This is not a completed activation of the T cell. So this dendritic cell is going to be like, let's do this. This isn't a viable, this doesn't benefit me at all. The way I like to think about it is, you know how you always see in the movies, and don't think about Trump, but you know when you see in the movies when they're like launching the nuclear weapons, they always have two guys with two separate key cards and they have to like put it in at the same time, have to go 3, 2, 1, and have to turn it at the same time. I like to think of it that if you don't have both of the keys, you can't launch the nuclear missile. So you're missing one of your key codes. So what does that mean? Well, this is a defective T cell, and the whole quote-unquote energy aspect of it means that it's going to apoptose. Because it realizes, the body realizes that it is worthless cell, so it's going to, well, it's pretty much worthless. So yeah, it is a mechanism for self-tolerance. Any questions on energy? Does that make sense to everybody? Yeah? Okay. Oh, there's mine. So I did have something to set up. All right. Good job, Past Pete. All right. So now, does anybody remember the different letters for the different isotypes?
G-A-M-E-D.
G-A-M-E-D, right? So, well, whatever. Okay. Can you tell me anything that you guys can think of about IgGs?
It's the most abundant one.
Abundant.
It's the delayed one, right?
Delayed.
It is in the secondary inflammatory response. You know.
It crosses the placenta, I think, and that's the one that provides for 6 months.
Yes. Provides immunity for infants for 6 months when they're born.
And it's effective against viruses and bacteria.
Yeah, so pretty much the only thing is that it also is the opsonizer or the neutralizer. Can anybody name the other opsonizer? I'll give you a hint. It's part of the complement cascade.
IgE?
It's part of the complement cascade. So it's one of the
C3D.
Yes, C3D. Okay, so IgG is seen here in the structure as a monomer, so it can only bind to antigens. So how about IgA? Any things from IgA you guys are thinking?
This is in secretions.
Mm-hmm.
It's in the GI tract, right?
Yes. So
Mucosal surfaces.
There you go, yeah. So how does a baby get IgA?
Milk, breast milk.
Right. So, right, it prevents bacterial and viral attachment in the mucosal surfaces, made in the Peyer's patches. Like you guys said, mucosal surfaces, Peyer patches are in the gut. It is mostly produced in the abdomen, but it has a lower concentration in the blood. Whereas here, this guy is IgG is most abundant in the serum. This one has a lower concentration in the serum. It can exist as a monomer or a dimer, as we see here. And if it has a dimer, it has what's called a J chain to connect it. And like you guys said, it has secretions in breast milk. It is in secretions and breast milk. And this is actually the mechanism for how mastitis doesn't affect the baby. Because when we have mastitis, we tell mom, hey, don't stop breastfeeding. It can cause to a retrograde infection. Keep breastfeeding, and I think we've discussed it before. How does baby not get sick with Staph aureus if the kid's basically drinking it? It's because this IgA completely surrounds all the bacterial cells, and baby has no problem because it prevents attachment to mucosal surfaces. Any questions on IgA? Okay, cool. What pathology is associated with this immunoglobulin specifically?
Giardia?
IgA is in the name of pathology.
Oh.
All right. If we have a deficiency in IgA, and it's
deficiency?
selective, it's called selective IgA deficiency, yes. All right, well, anyways, so really quickly, selective IgA deficiency is the most common immunoglobulin deficiency and it presents with anybody? No? It presents as an anaphylactic reaction when you are given blood products that aren't clean. So in a vignette, it would show up as a patient just got in a motor vehicle accident, their spleen's ruptured, and suddenly they're getting a transfusion of blood, and within minutes they have classic anaphylaxis. They have the rash, they have airway closure, upper respiratory issues, hives, urticaria, all that, and you gotta treat it the same way. You have to give them epinephrine, but it's because if they were never born with IgA, they never had it, and then you suddenly give them blood that had IgA, their immune cells are going to attack it as though it's a foreign antigen, and so they get an allergic reaction. Okay, IgA, what can you tell me about that one?
We just did IgA, so which one do you want?
I'm sorry?
You said IgA again, so...
No, I said IgM, and then M. N, and then M, and then M.
It's the most abundant, I mean not abundant, but it's immediate response. So that's like the first response.
What about shape?
This one's a pentamer.
Structure.
Yeah, it is a pentamer. It's found on surface of B cells.
Yes. So, excuse me. So it is in a primary response. It's the first guy that gets there. Pentamer structure, and it has a J chain also. So you just remember J chain if there's any kind of non-monomer structure. So if this is a pentamer, how many antigens can this molecule attach to?
10.
Yes, 20. So Yash said that it is present on B cells, you're correct, and when it's on B cells, it is a monomer, and when it's secreted, it is the pentamer structure, so it can be either. And it also fixes complement, and the promotes avid binding just has to do with the fact that it has 10 surfaces for antigens to bind to. As far as pathology associated with this, we already talked about hyper IgM syndrome, and that's just because this is kind of like the, I guess you could say the prototype immunoglobulin, meaning that if you don't have any class switching, this is the default setting. So if you have an error in class switching, like we had with CD40 or CD40 ligand malfunctions, then you're only going to be stuck with IgMs. Okay, how about IgEs?
These are the allergy ones that attach to mast cells.
Release histamine.
Yeah, so the mast cell degranulation, so mast cells release histamine.
They also work for worms by releasing eosinophils. Not releasing.
Okay, so that's what I was. Yes, that way. So the bind mast cells, they just patent in allergy to cause mast cell degranulation, and it is the main player in type 1 hypersensitivity reaction, and yes, parasite and helminth immunity with the help of eosinophils. Let's see if I have any notes on this. I'm sorry, they activate eosinophils. Sorry, they activate eosinophils. And this one has the lowest concentration in serum overall. And then IgD, it's unclear function, but it's found on B cells. And IgD, IgE, IgG are all monomers. Any questions on our immunoglobulin isotypes?
Okay, so to put things into perspective, so I know complement is usually like mostly activated when you have gram-negative bacteria, but is that the only time? Yes, right.
Yeah, I think so.
Defense against gram-negative bacteria.
And then,
MAC complex specifically.
but the B cell and T cell activation process still occurs.
You mean for other species?
Sorry, what?
You mean for like other species that aren't gram-negative?
So
B and T cell activation can occur with
viruses,
bacterial particles, any foreign antigen that
right.
macrophage can break down into little peptides and then present that peptide on the cell surface and say, hey, check this shit out. Is this normal? So I know virus and the bacteria on there. I don't know about hummus and worms. I think that's more Divius, like the IgEs and eosinophils job.
So after, like, so for example, we have a gram-negative bacteria, and the body is going to notice it as an antigen. So is it still going to do the
So I think
T cell, B cell activation and then go to the complement and be like, oh, complement needs to do this job here?
I think what you're confusing is innate immunity versus adaptive immunity. Because innate immunity, you're going to think of more of the complement system and how it's going to affect the body. But adaptive immunity is when you have T cells and B cells, and then antibodies that are already circulating.
Okay, so
It's two separate immunities that you're
right.
thinking about.
Yeah.
So think of innate immunity as like your macrophages, your neutrophils, your dendritic cells, your natural killer cells, things that can attack it really fast and kill it. But if it passes that innate stage, I would say that it's more of the adaptive side. That's when you have the T cells and B cells.
So if the innate part takes care of it, then there's no need for T cells and B cells.
Well, you're still doing memory after innate
you're gonna make it for
too.
memory.
It's gonna do both, because you also have
right.
the alternate pathway and the classical pathway for complement.
Yeah, because the classical pathway is mediated by IgG and IgM.
Yeah, so you're gonna have two things going on at the same time. Also,
at the same time, right?
So
okay, so it's not necessarily the fact that stimulation needs to occur in order for complement to happen, but it's the fact that they're both kind of just happening individually on their own at the same time.
Yes, because for the classic pathway, you need the antigens and the antibodies to be complex and going on, but you also have the alternate pathway where it can just react to things on the surface of the bacteria itself. So it can do both. And you also have the antibodies doing their thing at the same time, so it's like multi-pronged approach.
I think the way I think about it is it's doing the same as together, but one is taking a longer time and one is rather very quickly.
So I got the answer for you. This is in Kaplan Immuno.
I thought he was frozen.
Way to go find it.
Oh, am I? Oh, well. So both IgG and IgM can activate the system by this pathway, although IgM is more efficient. Although complement cascade is considered a component of the innate immune response, its overlapping stimulation of effector functions of cells of the adaptive immune response, as well as its role in the enhancement of inflammation, make it a critical effector system for removing extracellular invaders and concentration of antigens, just blah, blah, blah. So it is kind of like a bridge between the two immunity systems, like Yash is saying, the innate and adaptive. That's a good question. I didn't even think about that, actually.
Yeah, so what I have is, for innate, is kills pathogens as they're getting in the body, but adaptive. It's gonna develop over time, so it's not immediate. So complement will work hand in hand with adaptive immunity. And like Pete said, it's a process that's basically a self-check on itself.
Okay. And then, where the fuck do helper T cells go? So now where do, oh gosh. Okay, so I get, okay, what, the T1, the helper T cells, like, where do they come into the picture now?
Alright, so helper T cells, like, the helper T1 cells, their job is basically, like, you know, they're like cheerleaders that tell the macrophage, like, dude, get your shit in gear and, like, let's kill these things. They release the interferon gamma, which is, the way I describe it is, it's like giving a macrophage, like, a crazy energy drink that just gets it jacked up. I don't know, do you remember Moscatello, when she did the Kaplan analogy, she had, like, the Hulk hand, Hulk smash? She was talking about interferon gamma and how T helper 1 cells release interferon gamma, and they turn those macrophages into the Hulk. Do the Hulk smash on foreign invaders. So that's T helper 1 cells. And then T helper 2 cells was to help with IgE production of T cells. So helper 2 cells, they recruit eosinophils and promote IgE production. So they're on Hellman, pretty much. So they don't necessarily that's why they're the helper T cells. They don't participate in active killing. They just get everybody else riled up to do the killing for them.
Okay, and they are separate from, like, they can do their job without T cells being activated, or T cells need to be activated in order for helper T cells to do their job?
They're the ones activating the T cells.
They'd have to be activated because if you have a naive T cell, and you don't have, it doesn't have a specific thing.
I think
so a mature T cell is different from a helper T cell. They're not the same thing, right?
Okay, so I think, Pete, one thing that I probably would add to yours is when you talk about T cells being activated, they've already gone through their positive and negative selection, correct? Right. So they're either CD8 or CD4. So CD8 cells are going to directly kill virus infections. And then CD4 cells can differentiate into your helper T cells. And that's where you're going to get the separation.
Okay, so Yash is correct. And to answer your other question, Kelsey, the difference between a naive and an activated cell, it can be either CD8 or CD4. It just hasn't been activated yet.
Okay, yeah.
So it's already matured. It's already gone through the thymus, like Yash said, positive and negative selection, but they need that stimulation, activation, however you want to call it. Because the presented, so depending MAC1 or MAC2, either CD8 or CD4 cells can be activated. Yeah. So TA cells activate and produce cytokine, T helper cells activate and produce cytokine, and the T cytotoxic cells activate and is able to recognize and kill virally infected cells. Yeah, so they can't do that until they're activated. So they're just floating around looking for something to activate them, I guess, until an antigen is presented to them.
Okay, and then what was this question? Okay, so we have a CD4 cell, it becomes activated, and now it has this role of a helper T cell. Now, does it make, like, is its fate already determined to be a T1 cell or a T2 cell, a T helper 1, T helper 2 cell, or it depends on, like, what the body's trying to fight off at that point, or what that antigen is. And then it's going to be like, all right, I need to assume this role, like, if it's the helminth parasitic.
Well, that's going to be dependent on what cytokine is released to activate it. So, IL-12 will make T helper 1, IL-1 will make T helper 2. So, let's...
So now the cytokine is...
share my screen again real
when
fast.
You talked about...
So, right here, when it says the cytokine is released, whatever cytokines are released are going to determine what this T cell
needs, or what its role needs to be. Okay. Yeah. Okay, that makes sense. And wait, so the cytokine that's released, it could be interferon gamma or interleukin 12 for the T helper 1, and then interleukin 4. Okay.
I'm assuming it's situational because, IL-12 comes from macrophages. So if this guy happens to be near a bunch of activated macrophages, then it's going to be like a loop. This cell is going to activate the macrophage is going to activate the next helper cell. It's going to be this cycle until infection is cleared or whatever.
If you need an example, I'll give you one. So Th1 versus Th2 will depend on infection.
Yeah.
So Mycobacterium tuberculosis needs a strong Th1 response because think like what Pete said, macrophages. And once you secrete INF gamma from Th1 cells, it's going to basically stop production of Th2 cells. But like listeria doesn't need a strong Th1 response. So it will all depend on the specific bug or the specific bacteria. But those are, if you need an example, those would be ones that you could think about.
Okay.
So specific bugs will have specific reactions.
Okay, yeah, I get it. That makes more sense, guys. Thanks.
I think it has to do with whatever that naive cell is immediately next to.
Yeah.
Like if you were chilling next to a parasitic infection, you'd probably turn into a T helper 2 cell. If you were sitting next to a viral infection, you'd turn into a Th1 cell. So it's probably just whatever.
Or would it also depend on what the antigen is? So that's the same thing as you're saying.
Whatever it's sampling and what that causes to be released.
Okay.
Yeah, because you're assuming if you've got a viral infection, then the macrophage is going to present a viral particle to the T cell.
Yeah. And then the whole idea of how you were saying the whole macrophage becomes like a Hulk and just stomps on whatever the foreign invader is. So how does it work? So after it does its stimulation, does it come apart and then become the Hulk macrophage?
No, I think it's just its activity level is increased. It's phagocytic activity level.
Ability.
Yes. So I mean, you can just think of it like the macrophage was driving 30 miles an hour until it got interferon gamma energy drink, and then it's powering at 120 miles an hour suddenly, just slamming through as many cells or as many infected cells as it can.
But after it's done the whole co-stimulation,
it's gonna
they
go
separate
along
and go and do their own thing, right?
It's gonna keep eating other stuff around that's foreign as much as it can.
Yeah. Okay.
Because okay, Tulsi, great question. Because Yash just brought this up the other day. What happens if they don't separate and go their separate ways?
Energy?
Over selection, so they would just die.
Get what's called, what is it? Yash? A super antigen?
Mm-hmm.
Oh,
you get a super antigen that connects, whatever.
It doesn't need to present it on the TCR or MHC molecules. It just comes to the side and activates a bunch of T cells.
Yeah, so the super antigen is when they can't split apart and they just keep stimulating each other, and they just are secreting like mad amounts of cytokines that are just unnecessary, so you get an over-accessibility.
Oh, okay. Oh, gotcha. Okay.
Mm-hmm.
I think to answer your last question, you need to look at page 104. And what interferon gamma does to a macrophage, and what it tells the macrophage to kill the pathogen, right? Yeah. But then it also increases MHC expression and antigen presentation by all cells. So it's doing a multiple aspects. So.
Oh, just the role of interferon gamma.
Yeah. As far as, because you said what happens to the macrophage once it activates it, well, the Th1 is going to secrete interferon gamma. So then what that does to the other stimulation, essentially.
Stimulates macrophages to kill phagocytized
right.
pathogens.
So that's what the macrophage, once it becomes that Hulk, would do. But then eventually it can lead to that super antigen if it's not controlled.
Got it.
Oh, Th17. I forgot about Th17.
Yeah, so Th17 is involved in neutrophil chemotaxis and recruitment. And then,
right. It's important for mucosal immunity for your GI tract.
Yeah, if you guys have Treg cells in your book, right?
Mm-hmm. Yep.
Okay, yeah. And then the T regulatory cells are the ones that they depress the immunologic response. Basically, like the negative feedback saying, like, whoa, dude, you guys are getting out of hand. Let's just calm down. Sit your asses down.
Would Treg cells work for the, what's it called, super antigen thing from a bobber?
Probably not, because the problem with the super antigen is that they can't split it apart. So unless the Treg cells mechanism was to like snip apart cells, which it's not. With Tregs, what do they secrete? They secrete, IL-10 and TGF-beta. Those are like the anti-inflammatory cytokines. So you could probably only secrete so much IL-10 and TGF-beta against the super antigen, where the super antigen is going to win out because. But an absence in Treg cells is associated with pathology, which isn't in my book, but it is, at least in the new one, IPEX, IPEX.
I learned it today.
Okay,
P3 deficiency.
And DAC something.
Yeah, and it's like a pathology of the like 4 things.
Yeah, Fox P3. Is that the Fox P3?
Gene, yeah. I was actually also going to say, you know how you mentioned the whole pathologies about like, like when the B and T cells don't talk to each other type of thing?
The CD40 ligand.
The hyper IgM one?
Yeah, I guess I kind of also thought about like, I don't know if this is the right way to think of it though. Like a leash line when they don't, no, skid. When they have no B and T cell functioning. I guess that's not a matter of the fact that.
So SCID is, well, I have a bunch of words, but essentially you're not creating B or T cells.
Yeah. And then there's also pathology where there's only T cells but no B cells.
That is
X-linked.
Gamma-globulin
anemia.
Yeah.
Okay, so B Bruton's gamma-globulin.
Yeah, B cell count is normal, but functioning is lacking.
Right, because you're not, the B cells aren't maturing.
Yeah.
But in DeGeorge syndrome, you
Wait,
would
so
have-
is the maturation though? That's just the whole bone marrow thing where they go to school, right?
well, yeah.
Yeah, you have
Not the
pro
whole
you have
differentiation
pro B
part,
cells, you don't have B cells.
Right. They're not maturing.
Yeah,
Oh, so like the naive T cell, it's a pro B cell.
It's a
Before
pro
it
B
gets-
cell, and it's not in the peripheral blood. It's not in circulation.
Like,
It's
that's
stuck.
like even before it even. Okay, fine.
And then if you had something like DeGeorge, then you would have B cells intact but no T cells. Because you don't have a thymus, so you don't have a place for T cells to mature.
And SCID just has problems with everything, unfortunately.
Yeah, you're not going to have B or T cells. No lymph nodes, no tonsils.
I don't treat these people. IVIG. Okay, makes sense.
Yeah, you gotta give them what they're lacking. Feed it to them.
And bone marrow transplant. Oh, with no concern for rejection.
Because they don't have anything
To reject it.
to reject with.
Okay, guys, things are falling into place now.
Starting with that.
Yes, light bulbs are going up.